And John is from University of Birmingham, well known and in the field of ultra high temperature ceramics.
All right. Keep talking. Keep talking.
Keep talking. You did it perfect. Very good. Yeah. No, when setting up the program, of course, it was the idea. So I think.
Yeah, we better have.
I can help as well.
Yes, because that doesn't look like that.
No problem. Yeah. See, let's see. It's you. Yes. GB, that's you.
That's me.
Looks good. It works. Finally. Finally, I come also close.
Absolutely.
So, John, good to have you here. And
thank you very much indeed. So, I know this is a short course on refractories. We are now going to be looking at a slightly higher temperature. So we're moving up as a cross-sectional study. And there are many applications that require a combination of low mass, excellent properties at really quite high temperatures. 2000 to 3000 degrees centigrade is where we are looking with these materials. They've also got to be able to cope with shocks, mechanical and thermal shocks and cycles, and they've got to have excellent chemical resistance. And some, by no means all, but some of the applications, so nozzle flaps at the back of a jet engine, aircraft brakes, nuclear fuel cladding, very high temperature reactors, missiles, hypersonic flight. So these are the sorts of applications we're looking at when we look at these materials. So let's begin at the beginning. What exactly is an ultra-high temperature ceramic? Well, it's usually defined. There is no fixed definition. So everybody who publishes a paper defines it themselves. And amazingly, their paper then fits in their description, in their definition. But usually, it's something that can cope with more than 2000 degrees centigrade and under some other constraint, maybe an atmosphere or something like that, nuclear or whatever. And so you can do plots, but the ultra high temperature ceramics are non-oxides. And any non-oxide really has a craving, it has a desire to become an oxide. At the first opportunity, they are more thermodynamically stable, are the oxides. So you will develop an oxide. So it's the properties of the oxide that are as important as the properties of the non-oxide. So we've got a plot here. It's a plot of the melting points of the oxide against the melting point of the original material. And what we're going to be looking for are materials sort of in this end, because materials that are up there but down here are potentially going to have a problem. The most common UHTCs investigated to date have been the borides and the carbides of hafnium and zirconium. You will see why those are the most common very shortly. The borides offer a number of advantages: tunable densities, moderate CTEs, very good thermal conductivities. And that is something that is really quite useful to have, because if you're dealing with very high temperatures, what you want to do is get that heat out as quickly as you can from the system. So a high thermal conductivity is usually useful. Of course, you always want good mechanical properties. And as I say, they are non-oxides. Most of those applications you saw will have oxygen present. So you need oxidation resistance. Carbides, similar CTEs, generally slightly less good mechanical properties, generally less resistant to oxidation. But more crucially, when they do oxidize, they give off CO2 and CO, but mainly CO2, rather than B2O3. B2O3 goes through a liquid phase before it becomes the gas, whereas CO2 goes straight to the gas. That's a large volume of gas, and what that does is push off the oxide layer. Once that oxide layer has been pushed off, the technical term is spalling. Once that's pushed off, you've got fresh surface for attack. So the boride is more protective. Come on, move. Technology. The Starship Enterprise never has these problems. Right? I don't know.
No. It's correct. I don't know
I'd
either.
like to tap dance. There we go. Well done. Thank you. Lovely. Right. So some of the properties of these materials. Melting points. Not a huge amount different. Minor variations rather than more. Densities. Now, have a look. Densities are high. If you want this for an application that is going to fly, that is not good because it's extra mass. So the zirconium-based ones are by far the lowest density. So that's given them a lot of interest. The zirconia ones are also zirconia. The oxide has a fairly low melting point, relatively speaking, so that's more of a limitation. But then you've also got the elastic modulus, not a lot of difference. The hardness, again, tantalum tends to do less well, but again, they are all hard materials. Thermal conductivities. Now you can see the reason on the left-hand side of this plot why zirconium diboride and hafnium diboride are of such interest. Much higher thermal conductivities. They get the heat out. Coefficient of thermal expansion, again, depends exactly what you want here. A high value because you want to match with metal, or a low value because you don't need to match with metal. So it all depends then on your application. These materials, all of them, the transition metal borides and carbides, have strong covalent bonding. That gives us very good stability. For the carbides, we get high melting points, but the materials are a bit more brittle, which is always the problem with ceramic materials, as you know. Borides benefit from very strong bonding between the boron atoms and strong bonding with the metals. And the hexagonal close packed structure also helps to provide high strength. So that's sort of an introduction to these materials. Now, one of the things that many of those applications that I showed on that first slide or second slide come down to thermal shock. And this is something which many of us face in our daily lives. If you take something and you heat it too fast or you cool it too fast, you can have problems. And one of the things when you get into thermal shock, you realize is there are many equations. Lots and lots and lots of lovely equations to try and work out which equation is the best equation for my application. That's not always easy to find, but the key equations that we're dealing with here for crack initiation and propagation are given there. And the cutting to the chase, the important things are things like fracture strength, Poisson's ratio, elastic modulus, the toughness, of course, thermal expansion coefficient, and fracture surface energy. Although that fracture surface energy doesn't tend to vary very much. So a high strength is obviously good. A modest thermal expansion is good, but then it's less good for bonding to metals. A high thermal conductivity we know is good. It spreads the heat. And a high toughness. And UHTCs have these properties, except the toughness. Toughnesses are very, very limited. So this is some information. This is from the US Air Force. I do apologize. They never let me put the numbers on the plot. So I'm sorry about that. But for applications such as rocket nozzle throats or leading edges, so up there, what you have got in the pale blue, that's the front end of the space shuttle, the former space shuttle. What you've got in the red is a leading edge for a hypervelocity platform, something that will do Mach 5, Mach 6. It has to be sharp. If it's not sharp, you don't have the ability to steer. So it needs to be really sharp, and the consequences are shown here. So this is heat flux against position on that curve, and you can see the pale blue one is fairly gentle. There is a peak, but it's a fairly gentle one. But look at that red one. Absolutely. Very, very, very localized high heat flux. What that means is that if this is your leading edge, this is the bit that gets really hot. And if you then model that, actually it's this bit of that, and the whole of that is that. So it really is just a millimeter or two that's actually getting to the maximum temperature. And it's going to get there very quickly. So the heating rate is going to be very, very fast. So our ultra high temperature ceramics, they give us the temperature capability, they give us the thermal conductivity, particularly if you go for the zirconium and hafnium diboride. They give us the oxidation resistance just about, but fracture toughnesses are about the same as aluminium oxide, alumina, 3 or 4 megapascal root meter. That, and as you know, that's very low indeed. So thermal shock is a big problem. This is a nose tip, zirconium diboride silicon carbide. The nose tip that was made is the little shiny bit right on the end there. And it was made by the Italian Aerospace Research Center. It took them about 2 years to make. And then you can't read this. I do apologize, but this is it under test. And what you want to look at, if you could read it, is the difference between this and this, less than 1 second. So a couple of years of development, research, construction, manufacture, a little under 1 second to survive. Thermal shock is quite an issue. Now, in its defense, it wasn't just the thermal shock. I used to think it was just the thermal shock, but then I showed this image, which they sent me. I showed it, and in my audience was someone who had helped build it. And he said, yeah, it was thermal shock, but we also, in our wisdom, we decided to have it screw on, and that was not a good move. Right, so what do we do when we're lacking toughness in ceramics? We reinforce them. We put fibers in. And so if you think about it, we've got oxide fibers. They're limited to 1200 degrees centigrade, absolute maximum. You've got silicon carbide fibers. If you really push them, you might get 1800 to 2000, but they don't like it. But then you've got carbon fibers, and carbon fibers are really good, but they need protection from oxidation. So the idea of the ultra high temperature ceramic matrix composite, UHT-CMC, is that you capture the good behavior from the ultra high temperature ceramics. So that's the high temperature strength, the mass and so forth, the refractoriness, the oxidation resistance, and you combine it with the benefits from the CMC, which is the high temperature strength, the lighter weight, lower coefficient of thermal expansion, and good ablation resistance. So you try and get the best properties from one and the best properties from the other. There are many ways of making these things, but there are 4 main ones, and I'm going to just spend a few slides on each of the 4 main ways of making them. So the traditional way is to sinter things. That's how we make just about all our ceramics. We're happy with that. We've been doing it for thousands and thousands and thousands of years. So we're comfortable now with the idea of sintering. So you green form it and then you densify it. Now these are non-oxide, so we're going to have to use pressure, and hot pressing and spark plasma sintering are the 2 routes that are showing to be the most successful. But there are alternatives. For example, you can use reactive metal infiltration, you can use polymer infiltration and pyrolysis, or you can use chemical vapor infiltration. So what I've got next is a few slides on each of these 4. Essentially, though, you start with the fibers. When you're making any composite, you start with the fibers. You can have stacked 2D fibers. Just stack the layers one on top of one of another. Works well, it's cheap, it's effective. The problem is they have a habit of delaminating. And if you're flying at Mach 5, you really don't want your leading edge to delaminate. So you can move to needle 2.5D. So this is where you stack them, but then you send a needle down with a fish hook on the end, and it pulls one fiber from one layer to the layer above. It gives you a small amount of reinforcement in the Z direction. Or you can go to woven 3D. The whole thing is a woven structure. As you would imagine, cost increases as you come down. Performance increases, and so does cost. Cost is not linear, not by any means. So woven is much more expensive than the needled, and needled is more expensive than the 2.5D. But then you infiltrate with slurries, and then you sinter it, hot pressing, spark plasma sintering. You pyrolyze a monomer to the pit process. You use CVI, or you don't infiltrate with a slurry, but you infiltrate from a molten metal. So sintering. The basic concept, you've got two alternatives again. You can use a dry route, you can use a wet route. You can also, of course, use chop fibers. Now, chop fibers don't give you the same performance, but they do improve the performance, so they are worth considering. Focusing on the continuous fiber, what you will end up with is layers of material and layers of matrix in between them, and the whole thing is hot pressed together. But especially if you do it dry, you will end up with areas that are non-infiltrated and cracks running. Where you've got an area that's perhaps got an agglomerate in it, you can get a cracked matrix running between the two. So you can get, but these things, they have a microstructure, and you look at it and think, ugh, don't like that microstructure, but actually they do perform. They can perform very well. And the proof of the pudding is pull out. You'll get some pull out. To pull out means toughness. It means improved performance. You can use the chop fibers as well, and they're easier to process. We can use more conventional processing routes, but you still can end up with quite large floors. There's a nice 200 micron floor, or more than 200 micron. I'm sure we all know of good old Griffith back in 1924. Do you realize last year was the anniversary of his great theories? Wonderful person, not sure. But 200 microns, and that's going to cause all sorts of problems later on in your processing. So the advantages of sintering, it's a well understood route. We've been doing it for a long time. It's easy to vary the ceramic powder. You can add coatings to optimize the fiber matrix interface, which we always have to do. You get good strength, and crucially, it's possible to make large components. So this is one. It was made at the organization formerly known as ISTEC in Italy. They've changed names a year or two ago. I must admit, I can never remember the new one. But you can see there's a pair of hands, and this is a large hot press disc. We can make big components this way. So, and that's something that is quite valuable with ceramics, as any of you who work with refractories know. Making big components, in the lab, it's easy to make something this size. Making something this size is much more difficult, and keeping the same properties. But you have got limited microstructural control. You do need pressing. That limits your geometries you can form, and the sintering temperatures, even with hot pressing, 1800, 1900, carbon fibers really don't like that. That's what's left of a carbon fiber after being pressed. So the carbon fibers really don't like it. So that means you need sintering aids. That just makes it all the more complicated, but never forget it works. That's a crucial thing. Reactive metal infiltration, so it does exactly as the name implies. You take a metal, you melt it, you push it into the fiber preform. And the fiber preforms can again be 2D, 2.5D, 3D. The crucial thing here is the wetting. If it doesn't wet, you've got problems. So you have to have wetting. Not just wetting of the metal on the solid, but metal and the solid. When you've developed the reaction layer you want to create, that also has to be wetting. So there's a lot of understanding of wetting and chemistry that is required for doing this work. So the basic concept, and this has been done with silicon carbide. It's a commercial process. If you fly in an aircraft with GE engines, you will have flown with parts made by this route of 6.6 silicon carbide fiber reinforced. They've been flying since 2017. The LEAP engine has these silicon carbide components, and they're made by this process. But here we're talking of the ultra high temperature, so we're using molten zirconium. Not the easiest material to handle. Then you also put some boron-based powder, something that will give you your source of boron, and you rely on the reaction as the melt progresses up the preform. You've got that reaction happening inside it. It takes about 1900 degrees centigrade to get that to work with pure zirconium. That's a high temperature. The fibers don't like that temperature, and you get a coarse microstructure. So this was one little idea. This research was done at DLR in Germany, and they had one idea: let's put some copper in there, because if we have a zirconium copper alloy, that will now melt at 1500, and they get a much better, much finer microstructure. So the advantages: low cost. It's a fast process. It really is very fast. It's a matter of just a few minutes. Greater than 98% density. That is fantastic. And it's possible to add fiber coatings. Limited microstructural control. You do get fiber damage unless you can protect your fibers appropriately. Residual metal is common. Now, that's the problem. If it's residual zirconium, it's one thing. But when you've got the situation where you've added copper in there, now what they found was you've got phase separation. So you've got the zirconium diboride here, some zirconium carbide here, and they had a thin layer, literally very thin. That's 100 nanometers. So that's about a 1 nanometer, 2 nanometer thick layer. But its properties, straight down, because of that 1 to 2 nanometer layer of copper that was in the structure. So, but really good fiber, really good pull out. So this is a really nice, the material is lovely apart from that use of copper. What was needed now was to say, okay, copper didn't work, let's try something else. Unfortunately, the program ended. And that's what happens to research. You do some fantastic work, and then the money, your 4 years or your 5 years is up. I'm sorry. So it needs more work. It needs something other than copper in there. Polymer impregnation and pyrolysis. So this is where you take a polymer or monomer, and essentially it will, during pyrolysis, yield you a ceramic. This one is a proper commercial process again. And it's taking an existing proper commercial process and adapting it to ultra high temperature ceramics. It's used extensively for silicon carbide fiber, silicon carbide ceramics, SiC. Can it be adapted? So the advantages of this process, it's a very, very well established technology. The carbon fiber SiC process is already scaled up. This is a part. This is made in one piece. This is not bits joined on. That's all made in one piece. So it's really good because you don't have to worry about your joints and things like that. Complex geometries, as you can see, it's a near net shape process. And this is the size at which they work when working with silicon carbide. As I said, this is a proper commercial process. But again, you get a limited microstructure. And the big problem with PIP, multiple infiltrations are needed. So if we just skip back briefly, the process goes through, you coat your fibers, you wind your fibers, you decide to either use a hollow tube, or you cut the tube and you turn it into plates, you press it, and then you come to the pyrolysis stage. And in that pyrolysis stage, all the bits of your polymer you don't need burn off. All you want is the metal cations. And that's a lot of the polymer that burns off. So you get a lot of shrinkage. You've now got a lot of porosity. So you go back and you do it again. And you pyrolyze it, and more burns off. And you do it again, and you do it again. 10 to 12 reinfiltrations can be needed. One of my PhD students he got it down to just 4 in his particular system. And when we published the paper, people were saying, 4? Really? Don't believe you. Come in the lab and look. But it's even with 4, it's still multiple infiltrations, and that's your problem. And of course, you will never, you're chasing towards pure, fully dense. You'll never get there because even that last one is burned off. So you'll always have some porosity. And there's a restricted choice of precursors. If you want something for silicon, you have to avoid Starfire. Starfire is the industry standard. It's absolutely brilliant. It's great. It's wonderful. And because it's made in America, it comes with something called ITAR. If you don't know what ITAR is, keep your level of ignorance. It's wonderful. Knowing what ITAR is nothing but a big, big pain. So if you don't know what ITAR is, put your hands over your ears when somebody starts describing it. But essentially, it's all about movement of ideas and technology around the planet. And somehow the planet agreed that the Americans could control ITAR. So if you use any American product, even sometimes a specialist piece of American kit, your technology is now, the Americans can use it. So I get research programs, and in the title it says ITAR free. In other words, don't do anything that could bring us under ITAR. And then you look at all the possible routes you can do and you say, right, can't use any of those. I'll use this one over here. It really is a big pain. And that restricted choice of precursors comes about to an extent because of that. So then you've got the chemical vapor infiltration. Again, you can start with whatever preforms. 2 stages. One stage is you've got to put the slurry in there, and then the second stage is your CVI. We'll go into that. So the first stage to look at then is putting in the slurry. You can use vacuum infiltration, but your components will be small because you're just literally using a vacuum to suck your slurry into your preform. And if your preform is at all thick, it will go into the surface layers and no more. And you'll end up with an empty bit in the middle. That's no use. So we developed a process. This is Birmingham work. We developed a process based on injection. So you take your preform, whatever type, 2D, 2.5D, 3D, and then you plunge a needle in. And then as you withdraw the needle, you're pressing down and you're squirting the slurry, and you squirt it locally where you want it. So you can put in the ceramic slurry into your preform. Now, once you've developed that process, you say to yourself, well, do I have to always use the same matrix? Can I put different things in different locations? And it occurs to you very rapidly, I can do this as often as I like. And with each needle, I can put a different slurry. I can now engineer what I want, where I want it. Now, you do not get a nice, sharp, hard edge like that. This is my inability to use PowerPoint in a sophisticated way. What you will get is very much a blur because this has gone in as a slurry. Slurries mix. So you'll have a region around that where it's nicely mixed. Actually, that's really, really good because it doesn't give you a hard interface. So it's less chance of things falling apart because of it. So now you can literally put what you want where you want it. So this, you'll see this sort of shape several times. This is what's known as a little jet vein. It's about that big, so it's not awfully big. But now you can have one material, let's say hafnium diboride, that gives us 3000 capability on the outside. Zirconium diboride, that gives us 2000 degrees centigrade in the middle. And then you can have something else entirely, like silicon carbide, in the little stem. That's all one piece of fiber. It's not, again, it's no joins. It's all one piece. So you can put what you want where you want it. As I said, you don't get a hard interface. So this is the hafnium, this is the zirconium. And you can see in this region here, you've got both and they're nicely mixed. So you don't have a hard interface. And the reason why you want to do this, hafnium diboride, yes, it'll give you 3000, but it's 10.5 grams per cc. It's dense, and it costs about, I apologize, I've used pounds. Normally I would have remembered to convert that to euro, but that's 1600 euro per kilogram. Zirconium diboride, 2500, just over half, 60% of the density. We're now down to 300, call it 400 euro per kilogram. Silicon carbide down to about 1700. Again, we've halved the density. Now we're down to about 100, 120 euros per kilogram. So you can make big, big weight savings and you can make big, big cost savings by only putting what you really need where you need it. Then you've got the CVI part, chemical vapor infiltration. It's a process where you basically take a gas, you heat the gas breaks down and gives you a solid. It's the same basic principle as chemical vapor deposition. That gives you a coating. In this case, we're actually passing the gases through a preform and it's depositing within the preform. It is a fully commercial process. Carbon-carbon composites for aircraft brakes. Every time you fly on a commercial airliner, those brakes are made by this process. And for silicon carbide, SiC composites being used for aerospace. So the process works. There's all sorts. You can use methane to give you carbon. You can use trichlorosilomethane to give you silicon carbide. You can even use, and we have done, zirconium chloride and boron chloride to give you zirconium diboride. So there's a lot of possibilities that you can use there. So the advantages, it's near net shape, wide range of compositions. Processing temperatures are beautifully low. No more than about 1,000 degrees centigrade. No damage to your carbon fibers. The matrix you get is pure and fine grained, which is great, gives you good strengths. And you simply put one gas through and there's your interfacial coating, and then a different gas and there's your matrix. So terribly efficient in that respect. The disadvantage. You knew there was a disadvantage coming. There's always a disadvantage. It is slow. I mean, seriously slow. When you heat anything in a furnace, what's the hottest bit? The outside. So you heat really slowly. You heat to 1,000 degrees centigrade at something like 1 degree heating rate per minute. So that's 1,000 minutes to get to temperature. Even then, you've got temperature gradients. And temperature gradients mean that where does your deposition happen? It happens on the outside of the body. So the outside is where you deposit first, you partly fill it, you get a crust on the outside, you've stopped your channels being open. Now you can no longer get the gases through. The gases are just going around the part. So you stop the process, take the parts out, machine them, put them back in, and start it again, heating it at 1 degree per minute up to 1,000 degrees. Very, very slow. And you need to do that 2, possibly 3 times. 1,000 hours to make each aircraft brake. But they make them in enormous great chambers that will hold 1,000 parts. And it takes 2 to 3 months to make each aircraft brake. But you're making them in volume, it is economical. Now, if you want to use this process, not to make thousands of aircraft brakes, but to make tens of parts, the economics are terrible. So we need to speed up this process. Many people, many people, pressure and concentration gradients, temperature gradients, force flow, pulse flow. Many people have looked into how can you speed up the process. None that I'm aware of are now commercial. At Birmingham, and before I was at Birmingham, we looked at microwaves for silicon carbide fiber preforms. Silicon carbide fibers absorb microwaves very readily. And for carbon fiber preforms, we use radio frequency RF. Again, carbon fibers absorb it very easily. Now, what happens now is that the inside temperature, you get inside out infiltration. The inside is the hottest. The outside is the coolest. You get the deposition in the middle of the part, and then it goes outwards. That eliminates premature pore closure. You don't have to stop the process machine, start again. It's one run through, much shorter processing times. With silicon carbide and microwaves, 10 times faster, 100 hours instead of 1,000 hours. With RF and carbon fibers, 40 times faster. You can now do it in 24 hours to make a part. Don't ask me why 10, why 40. I haven't got a clue. Theory says they should be the same. They're not. So something which at some point, someone will give me some money and we'll try and find out why. So this is just one example. Carbon fiber, zirconium diboride, carbon as your matrix, 2.5D preform, gas flow going through. There's the part being heated. You can see it's hottest in the middle and coolest on the outside. 21 hours later, you've got something which is 10, 11% porous. Now with CVI, you will always end up with about 10% porosity. That's the limitation of CVI. You won't get more than 90%, 91% dense. But there's no difference between the microwave and the RF and the conventional. They're both very, very similar. And the properties, you wouldn't be able to tell which route had been used. And that was really important, that people found that the product was the same. We had a PhD on this funded by the US Air Force. And what they really wanted to know was, is there a difference? And the answer was no, there is no difference. So this again is our little part. That's our standard part we make. Why do we make it? Because it's complex shape. And therefore it gives us the ability to really show we can do things. So that's our part. That one is actually full of hafnium diboride. Purely no grading, this was done before we did the grading. Hafnium diboride, this is not something we could do, but we got a British company called Kinetic, and they did a formal cost analysis, and they found they might be 150 euros each. And everybody was expecting this analysis, including me, to come out at 1,000, 1,500 euros each, and it came out at 150. So many people checked the maths and checked the thinking. It was quite right. And this is based on a 0.4 meter cube chamber. So it doesn't have to be an expensive process. So it's a near-net shape process, reduces processing time up to 40 times faster with carbon fibers and RF. That reduces the energy, of course, that reduces the cost. Materials can be easily tailored. We can use that injection route. Scale up is now underway. We used to make one of these things at a time. We can now make up to 40 at the same time. But that's as far as a university I ever want to go. You know, it's been a painful experience the last 2 or 3 years scaling up. It really has. It's not something that I think universities generally are good at. Some people are really good at it. For us, it's been 1 step forward, 2 steps back, 2 steps forward, 1 step. You know, it really has been quite a problem scaling up, but we're getting there as part of a particular project. So we get the best microstructure, low temperature process, no damage to the fibers, possible to deposit coatings by simply having gas A first and then gas B, up to 40 times faster. Even 24 hours, it's still a slow process. We mustn't get carried away. It's still a slow process, 10% residual porosity. Scaling up is still underway. It's still underway. But we've been making 2 shapes. This one, which is our demonstrator, and we've also been making rocket nozzles. Now that's for a commercial company, a civilian company in Europe. Next week, they're testing them in Stuttgart, and I'm in Dresden. And it's a 3-hour drive from Dresden to Stuttgart. So I'm still thinking, yeah, do I leap in a hire car and do I drive to Stuttgart and watch 1 or 2? But these are full size. This is why we had to scale up. Full size rocket nozzles. And they've got a tame rocket. They have bolted to the ground in Stuttgart. And then put one of ours in. And it's a proper rocket test. So we'll say we've done little tests. The University of Naples, as you will see, does baby tests, but this will be a full success. My fingers will be crossed. Costs appear to be surprisingly cheap. So if we then compare, how do these things compare? Well, you've got the basic materials that you start with, and then you look at them in terms of the properties coming out. Sintered are very good. Notice how the strengths go up with temperature. Significantly, 120 to 200, 178 to 316. PIP is really quite porous. Look at it, 25% porous. But you're getting much better strengths. We were surprised at that, but that's what came out. RF CVI are the lowest numbers that come through, but they're still perfectly reasonable. Most people, when you say to them, for applications, what strength do you need? They say, oh, about 100 megapascals. And we're nicely over that sort of thing in flexural strength. So, you know, there are advantages and disadvantages. So these things give us good properties. We have a good performance generally that will get good strengths and good fiber pull out. I noticed the time, so I'm going to speed up just a little bit. We've looked at the thermal properties. We've mapped out the thermal expansion, thermal diffusivity, thermal conductivity, and heat capacity. So these are now able to be given to design engineers who can work on parts. You've got to test these materials. There's a number of ways of different testing them. I'm just going to look at a couple very briefly. The oxyacetylene torch test and the arc test. So the oxyacetylene torch, it's literally exactly what it says. It's an oxyacetylene torch, which is by your sample. And you can see some of the details, typically 10 millimeters from the flame tip, but you can make it more. Typically rotated in, you can go up to about nearly 3,000 degrees centigrade with an oxyacetylene torch, 2.5 with oxypropane. Heat fluxes, heating rates, as you will see, 1,000 degrees per second. It's a subsonic test. Those are the two, the oxyacetylene and the oxypropane. And then this is an actual test. And then what we can do is we have a filter, we can actually watch what's happening on the surface while we're testing. And the slowest part of the test, waiting for the damn thing to cool down so you can put another sample in. So it's a test, 5 minutes, 10 minutes, half an hour, whatever you want, and then wait 4 hours for it to cool. And then these are your heating rates. As I say, 1,000 degrees a second and holds it up. It's also an indication of thermal conductivity because that black line that's below, that's carbon-carbon, and that actually is a very high, the highest thermal conductivity, so the heat is most dissipated. So it's interesting. And then you can test at an angle as well. Instead of testing everything at 90 degrees, you can test it as a glancing as well. And you can have any angle you want, just about. Then you've got the rocket test. These are done at UNINA. This is the University of Naples. And you can see the sorts of damage that the nozzles took. These are baby. These nozzles are about this size, nothing like the full-size nozzle. And then you've got the arc jet testing, which is done at DLR. It's a wonderful test. It's the closest to real life. 150 megawatts. It's 10 times the heat flux of an oxyacetylene torch. It's the most realistic. It is not cheap. Tens of thousands of euros per run. NASA has one, AFRL in the States has one, DLR has one. We use DLR for ours. There's one of our samples being tested. These are sintered long fibered. That's a sintered one. That's from ISTEC. And then this is a CVI based one. This is where my persuasive powers actually worked for once. So we did 2 tests on the same sample. That was agreed. And the results, which your top left-hand corner, were so good that I persuaded, oh, let's do a third. Come on, let's do a third. We got a 3rd test. Oh, go on, let's do a 4th. Come on, let's do a 4th. Come on, you want to see the results. We got a 4th. Come on, let's do a 5th. No chance. So we have now got significant amounts of data on the mechanical and physical properties of carbon fiber reinforced ultra-high temperature CMCs. It's still patchy. There are so many different approaches. There are so many different things. But nevertheless, we've got some good idea of what works. We can get very good strengths with sintered and higher thermal conductivities, but with the UHTCs, but much worse thermal shock resistance. We know the hafnium-based materials offer higher performance than the zirconium-based, but they're twice the density, 4 times the price. And the carbides are also slightly weaker, and the oxide layer is more like a spot. So we've got some general ideas now. And as I say, with these tests we've been making of rocket nozzles, which the tests happen next week now, which is quite exciting. Who knows? Maybe in a year or 2, you'll actually see these things in commercial use. That's me finished. Thank you. Sorry for it.
Thanks, John, for this nice and lively lecture about your profession in these ultra-high temperature materials. Yes, directly questions, I think. Yeah.
Hello, John. Hi, Victor.
How are you? You didn't mention about work of fracture, and you said that it's about the same. But as understood regarding thermal shock, you don't take care too much for crack initiation, but for crack propagation.
I don't work on ultra-high temperature ceramic. For one thing, I don't have a hot press or a spark plasma sintering. So if I want to do that work, I have to go somewhere else. University of Sheffield has an SPS, so I tend to use that. It's an hour away on the train. So I don't do that work. Our work is at Birmingham, but people are working. For example, Bill Fahrenholtz in the US. He doesn't work on the composites. He only works on the ultra high temperature. He's got the facilities. He's got the capabilities. And again, they're wonderful materials. You just have to make sure that thermal shock won't be an issue at all, because they're no better than aluminum. So as long as you make sure your application doesn't have any sudden sharp changes in temperature or local gradients within your component, you're fine. You're fine. A question in the corner?
Yeah, we need the microphone to have for the internet. Yeah, but there are also online participants.
They're online people, remember.
It's my practice this morning.
Okay, Ino Jung from Seoul National University. Nice talk. I'm doing thermodynamics, and I want to always design the materials based on the degradation, mechanism and etc. But when you actually show me today, I mean the hafnium boride, for example, if it is perfect microstructure, is it just as it is good enough for the most of the application? What do we have to still design some of the composition, for certain perspective?
We use it. I've moved back to the mics to speed things up a bit. We use it just as it is, and remember that in the CVI system, the matrix is not sintered, so it is still a loose powder. And now that reduces our strength, because our strength is fundamentally the strength of the fiber preform, which is why we're getting 100 megapascals and 150 if we get it absolutely right. But it's not a desperately strong. You saw that both the sintered and the PIP gave us much stronger materials. That's a limitation. On the other hand, it's really good at thermal shock. You can't thermally shock it. 1,000 degrees a second, no problem. It just sits there and smiles back at you. So you really, they're the same material, but they're different materials. And you really have to say, what application can my materials work in? So rocket nozzles is a possibility. Leading edges is a possibility, because they don't need to be structural per se. They just need to be able to contain things. And a rocket nozzle, how long is a rocket nozzle used for? 30 seconds, a minute, and the rocket's up there. So it's not as if we need this sort of performance for an hour or 2 hours. We have got a ongoing project, which is for something where the target is 50 hours of performance. There our strategy is different.
Thanks a lot. All right. Yeah, then John, thanks again.
Okay, thank
For
you.
joining us here today, this morning. I hope you might stay even for further questions.
No, I will do so.
That's
I'm my
nice.
good friend.